We're going to finish up Chapter 11 by looking at Section 11.11 and its atomic properties in the periodic table. So this information I know that you're already familiar with. We know that metals tend to lose electrons and to become more like their noble gas that's before them, and they are positive ions that they form, and our nonmetals tend to gain electrons, making them negative when they form an ion. So positive ions here and negatives over here. Again, just a review. We're going to talk about ionization energy. This is the energy required to remove an electron from a gaseous atom or ion. So here's our element, and it's gaseous, and we're going to remove this electron from it, and it's going to become positive. And that requires energy. So the ionization energy is the energy required to remove that electron. Here's an example. Taking magnesium to magnesium plus 1, to take that one electron away, the ionization energy is 735 kilojoules per mole. So it takes 735 kilojoules to remove a mole of electrons from the magnesium atom. To remove that second one, the ionization energy is 1,445 kilojoules per mole. It's going to be that electrons that are left are attracted to that nucleus even tighter than they were before, so it's going to take more energy to take the second one away. So it's referred to as the second ionization energy. Well, let's look what happens when we take that ion, that magnesium plus 2 ion, and we try to take a third electron away from it. It goes up to 7,730 kilojoules per mole, and it has this little asterisk here. The core electrons are bound much more tightly than the valence electrons, and this is getting into a core electron here with the magnesium atom. So magnesium has 2 electrons in its outer shell. It's easier to take those 2 electrons away than to take the inner core electrons away. So the ionization energy for the third one goes up quite drastically. In general, as we go across a period from left to right, the first ionization energy increases. Remember, this says in general, and I know that that's kind of frustrating sometimes because we don't have the same exact pattern all the time. So again, we use the word in general. So for the most part, as we go across the period from left to right, the first ionization energy increases, so it gets more. So the question is why? Well, there's a couple of different reasons. Electrons added in the same principal quantum level do not completely shield the increasing nuclear charge caused by the added protons. So it causes the ionization energy to increase. The second reason, electrons in the same principal quantum level are generally more strongly bound from left to right on the periodic table. So it takes more energy for those electrons. So let's look at it visually. So the energy required to remove an electron increases across a period. Because that energy required to remove an electron increases, the ionization energies generally increase across a period as well. In general, as we go from top to bottom or down a group, the first ionization energy decreases. Let's see why that would happen. The electrons being removed are, on average, farther from the nucleus, so it's easier to take them away, so the ionization energy decreases. So the electrons are further away from the nucleus, kind of like a parent who has, let's say, instead of 2 kids, 1 for each hand to keep control of, they have 15 kids. So the ones that are further away from them are harder to hold on to, easier to get rid of, or to lose, I should say, not get rid of, but to lose. So the energy needed to remove the electron decreases, therefore the ionization energy decreases down a group as well. So this concept check says which atom would require more energy to remove an electron and why. And if you look at the answer, which is chlorine, sodium and chlorine are on the same principal energy level. And they are in group 3. So sodium's at the far left and chlorine's at the far right. So the ionization energy increases from left to right. We start to see fuller shells as we go toward the noble gases. So chlorine just lacks 1 electron from having a full orbital, whereas sodium, it's easier for it to give up 1 than to gain 7. So it's going to take more energy to take away electrons from chlorine because chlorine is going to want to grab an electron and become negative instead. So they're in the same principal quantum level, and they're generally more strongly bound from left to right on the periodic table? Which atom would require more energy to remove an electron, and why? And the answer to this one would be lithium. Lithium and cesium are both in group 1, and lithium is at the top while cesium is at the bottom. That means that lithium is going to have a stronger hold on its electrons than cesium. Cesium has so many more than lithium that it takes less energy to remove the ones that are further away. Let's look at atomic size. All right, in general, as we go across a period from left to right, the atomic radius is going to get smaller. The reason is the effective nuclear charge increases, so that charge of the nucleus increases with number of protons. Therefore, the valence electrons get drawn closer to the nucleus, and it causes the size of the atom to decrease. In general, atomic radius increase going down a group, and that should just make sense. The orbital sizes increase in successive principal quantum levels, so 1, 2, 3, 4, 5, 6, and 7. So as the overall size changes, we end up with a larger radius. So left to right, atomic size decreases in general. Top to bottom, the atomic radius will increase. So atomic size, you have that across here at the top. Atomic size decreases left to right, and the atomic size increases top to bottom. So which should be the larger atom and why? Sodium and chlorine. Here again, sodium and chlorine are in the same row, the same principal quantum number row. Sodium's on the far left, chlorine's on the far right. So the larger one's going to be sodium because those electrons are going to be pulled in by a greater nuclear force as we go left to right. Which should be the larger atom and why? Lithium or cesium? Again, lithium's at the top of the first row and cesium's at the bottom of that column. So lithium is the principal energy level 2, while cesium is in 6, therefore making cesium the larger atom. Okay, I want to go back to this slide. I know you don't have another one of these at the last of your packet. We're going to go back to this slide and a couple things that I want to point out. First of all, when we were talking about both metals and nonmetals earlier in the lecture, a couple things I want to point out. First of all, we see that although properties of metals and nonmetals vary, in general, the elements that can most effectively pull an electron away from a metal are going to occur in this upper right-hand corner of the periodic table. And that makes sense because our most electronegative element's up here with fluorine, and it has an affinity for those electrons, so it's easier for it to take electrons from metal than to give up its electrons. Another general rule that I want to point out is that the most chemically active metals are actually down here in this corner of the periodic table, in the lower region of the periodic table. And that should make sense to look at that and see that the most active metals are down here because these are the ones that lose their electrons the easiest. The atomic radius is larger, the ionization energy is lower, and they lose their electrons easier than the rest of them. And then up here, these gain electrons more rapidly.